Hi everyone. In today's lesson we're looking at Chapter 7, Section 1, Rigid Motion in a Plane. Our objectives are to identify the three basic rigid transformations and to use transformations in real-life situations. Our standards are G-code 2, 3, 4, 5, 6, 7, and 12. Let's start with some vocabulary. Our first vocabulary word is image. An image is a new figure that results from the transformation of a figure in a plane. So looking at these examples, there are three kinds of transformations that we're going to learn in this section. But with all of these transformations, one thing to know is which one's the original and which one is the transformed image. If you notice, these points over here, B, C, D, E, F, do not have an apostrophe by it. So these are all of the original points of this figure. Same over here, H, I, J, that's the original points of this figure, and so is K, L, M. After performing a transformation, all of the points have an apostrophe by it, where we've got B prime, C prime, D prime, E prime, and F prime. The transformed point has a prime next to it. So that's how you know that a transformation has occurred. Pre-image. A pre-image is the original figure in the transformation of a figure in a plane. So a pre-image is the original image. So this one over here is our pre-image because it doesn't have the apostrophe by the points. So same over here. So it'll say B, C, D, E, F, and here it'll be H, I, J. So, and here is K, L, M. Those are our pre-image or original figures. Transformation. A transformation is the orientation that maps or moves a pre-image onto an image. We know of four kinds of transformations: a reflection, rotation, translation, and dilation. Isometry. An isometry is a transformation that preserves length. Isometries are also called rigid transformations. So what this means is the shape of the pre-image and the image are the same. It does not change. We have three types of rigid transformations or isometries. They are reflection, rotation, and translation. Dilation is not an isometry because in dilation, the size of the image changes. It can get bigger or smaller. Example number 1, naming transformations. Use the graph of the transformation at the right to name and describe the transformation. Looking over here, here's our original image, A, B, and C, and we can see from A to A prime, and B to B prime, and C to C prime. This is our image. All we've done is we've taken it and moved it to the right and up. So all we're doing is sliding, and we know a slide is also called a translation. So you can imagine that the image was moved by sliding triangle ABC up and to the right. B, name the coordinates of the vertices of the image. So basically, where are each of these points located? So we're looking at the image, not the pre-image, so anything that has the apostrophe on it. A prime over here is located at x equals 1 and y equals 3. B prime is located at x equals 4 and y equals 7. C prime is located at x equals 4 and y equals 3. C, is triangle ABC congruent to its image? If this was a translation, then it's an isometry, meaning that the size of the image and the pre-image are the same, but we can verify that. So let's just double check. Going from A to C, we notice that we have 1, 2, 3 units. So let's make sure that A prime to C prime has 3 units. So it's going to be 1, 2, 3. Yep, that works. Also, let's double check B and C. So B is 1, 2, 3, 4. I'm just going to write that this is 3 and 3, and this is 4. Let's double check over here. 1, 2, 3, 4. Yep, that's 4 units. Now it looks like this is a right triangle, so you could use the Pythagorean theorem and check to see that 3 squared plus 4 squared and then its square root should give you this length, which is 5, and this would be 5 as well. So yes, triangle ABC is congruent to its image, triangle A prime, B prime, C prime. One way to show this would be to use the distance formula to find the lengths of the sides of both triangles, then use the side congruence postulate. Alright, checkpoint problems 1 and 2 are yours. In this problem, you are to name and describe the transformation and then say if triangle ABC is congruent to its image. So here's our problem number 1 and problem number 2. Example 2, identifying isometries. Does the transformation appear to be an isometry? Remember, isometry means that the size of the image does not change. So their pre-image and image are the same size. Looking at example A, we're going from this gray shaded figure, which looks like a square, to a rectangle. And you can see visually that the size has changed. So no, the image is not congruent to its pre-image, so it's not an isometry. B, going from the shaded pentagon to the unshaded, or vice versa, you could see that both of the images have the same size. So yes, it is an isometry. The shaded pentagon is reflected in a line to produce a congruent unshaded pentagon. And finally, looking at C, we got a trapezoid that is translated over here, and visually you can see that it has the same size. So yes, the shaded trapezoid is translated down and to the right to form a congruent unshaded trapezoid. All right, checkpoint number 3. Does the transformation appear to be an isometry? Explain. Example 3, preserving length and angle measures. In the diagram, triangle JKL is mapped onto triangle MNP. The mapping is a reflection. Given that triangle JKL is mapped onto triangle MNP is an isometry, find the length of line segment NP and the measure of angle M. One thing I wanted to draw your attention to is this arrow over here. This arrow just means that it's mapped to. What that means is that each point has a matching point on its transformation. So say for example, J would match to M, K would match to N, and L would match to P. The statement triangle JKL mapped to triangle MNP implies that J is mapped to M, K is mapped to N, and L is mapped to P. Because this is a transformation that is an isometry, meaning that the size does not change, we know that the two triangles are congruent. The lengths are the same and the angle measures are the same. So we're looking at line segment NP, which is equal to KL, and we know that KL is 9, so NP is also 9. And the measure of angle M is equal to the measure of angle J, which we know angle J is 48 degrees, so then the measure of angle M is 48 degrees. All right, checkpoint problem number 4 is yours. Triangle ABC is mapped onto triangle XYZ. Given that triangle ABC is mapped onto triangle XYZ is an isometry, find XZ and the measure of angle Y. All right, that's it from me. I'll see you all soon.